The next speaker will be Brent Garry, as I mentioned before, and he's gonna talk about what I hinted at already, the distribution and geologic context of boulders and outcrops along the connecting ridge at the Lunar South Pole, connecting ridge at the Lunar South Pole exploration site. Take it away, Brent.
Okay, thank you. Sorry for the delay. So I'm going to follow up based on the last talk and talk about more of a specific map of boulders and outcrops along this connecting ridge region in the Lunar South Pole. So Apollo returned, several beautiful images as we see to the right, where they visited multiple boulders at each landing site. Some kind of small boulders, and some boulders that are large, towering way above them. Some were along the crest of crater rims, and some had rolled down the hills, like at Station 6 from Apollo 17. So lots of reasons to kind of target and think about visiting boulders for Artemis. Once we start figuring out where we want to go, we want to look at what geologic features are located, where they're located, and how that can help us inform our science mission and planning. Now, depending on your point of view, boulders might be good for science, as was on Apollo. And if we even better, if we can get to outcrops that were observed, like at Rima Hadley, but a little too difficult to sample there. So we want to be able to target those for our traverse planning, since we'll still have fairly limited time during these missions. But from a different perspective, from a landing perspective, boulders can be viewed as a hazard. We're coming up on the anniversary of the landing for Apollo 11, and you may recall Armstrong saying, "Hey, there's a pretty rocky area there," as he dodged a boulder field associated with Rest Crater. So I encourage you to jump into Ben Feist's Apollo in Real Time for Apollo 11 shortly after this session to catch that landing, and you can see that boulder field right there in the window of the LEM. So each landers will have a ground clearance limitation, so we want to know not only where these boulders are, but how big they are. And so a spatial map of these boulders and blocky craters will help inform the placement of various landing ellipses in an exploration zone. So for this case study, we went to the connecting ridge, or we're studying the connecting ridge, which is that little area between Shackleton and Des Gerlache, known for its high illumination along the crest ridge as determined by Mazarico et al., as well as its access to permanently shadowed regions. So zooming in, our study area is about a 16 by 16 kilometer section. There's a top-down hillshade view on the right and a perspective view that looks along the crest of the ridge towards Shackleton, the rim of Shackleton crater there. There's a little letter A that marks the same crater in each image. You kind of get a view of where you're looking at. So we really wanted to document how many boulders and other features are in this area, and build on previous studies that have looked at boulders at the Apollo sites as well as along the rim of Shackleton crater. So what are we looking for? These, whereas Hannes made more of a geomorphic map and kind of beautiful polygons, we're looking at making more of a point feature map. So we want to look at boulders, which we can identify here on the bottom left with kind of these bright albedo faces, these really long shadows that come from the extreme lighting at the Lunar South Pole. And you notice it has an opposite shadow pattern from the crater that's nearby. We also want to look at outcrops or exposures, like kind of these mounds that have these illuminated faces. Sometimes they might have even more of a layer-like appearance without a shadowed tail. So we want to identify where there might be exposures. And we also want to identify the location of blocky craters, like we see here on the right. So kind of things to avoid with larger extent of a boulder field, things that we want to avoid during landing. So these are just a few examples of what we've been mapping. To do this, we started with the NAC average mosaic over here, which is a work of art in itself. But there are a few artifacts, and some of the areas are washed out, so it's difficult to see all the boulders. So we processed a series of mosaics. Essentially, we filtered them out in LROC Quickback by their solar azimuth to give different lighting conditions, lighting as well as slightly different resolutions. So between 0.5 meter per pixel to 1.6 meter per pixel. So this shows the features that the mosaics that we looked at in ArcPro to map the boulders and outcrops. So here's the map off to the right. As it currently stands, we've mapped close to 1,500 different features. Some of the main things we look at, the green triangles and yellow triangles, are boulders that we think are pretty definite, and the yellow triangles are kind of possible boulders or something there. But might not be sure if it's just kind of something buried or if it's actually a rock sitting on top of the surface. We've mapped outcrops, which are the orange squares, which are located all throughout. And then the pink circles mark the blocky craters. This is viewed about 1 to 50,000 on the right. There's a little yellow triangle right up here that shows this inset. So when it's zoomed out, all these features look like they're right on top of each other. But when you kind of start zooming in to looking at this NAC image, you can see how they're spaced out. And even this closer little inset, which is marked by the yellow arrow, you can see kind of maybe something might be an outcrop or boulder next to about 3 different boulders right there. So just to give you an idea of what these things look like when you start zooming in and how spaced apart they can be. Just an example of some of the blocky craters. This is one of the more denser areas of the map. You see 2 craters right next to each other. I'm just going to flip between them so you can see where the boulders and some of the outcrops are. We've also done some polygon features where we've marked the crater rims as well as the extent of these boulder fields that are associated with these craters. Once we have this map, you can be like, hey, what can we do with all this information? So we can do the slope map, say, hey, where are boulders that are on slopes less than 10 degrees or less than equal to 10 degrees, which are, might be something easier to walk to or get to for a crew or even a rover. You also might want to say, hey, where are the boulders in the higher illumination areas? So where are boulders that are illuminated greater than 70%? So we can kind of query the data sets and get a little subset map of just those features that are boulders less than 10 degrees and boulders in the higher illumination area along the crest of the rim there. We can also say, hey, where features are close to the permanently shadowed regions. So we can create a little buffer, maybe 100-meter buffer around the permanently shadowed regions and figure out which boulders we might be able to visit as we go into PSR. Now, one of the key things about these boulders, it's easy to measure their width, it's easy to identify where they are, but trying to figure out how high they are, how tall they are, can be difficult, especially with the extreme lighting. So the terrain has a very big influence on the shadow measurement. So if you just take a measurement of the shadow without factoring in the change in the terrain, you can get very different results. So just a simple 3D graphic model off to the right, you see the same boulder against the hill or on a flat area or at the crater rim. And on the right, you're looking top down as if it's a feature or a spacecraft. And you see just how the shadow changes if it's going up a hill on the flat area or down into the crater. So this is important because as we take measurements, if we just measure the shadows on this cluster of boulders here, it would give us a range of, it would tell us that it's about 20 centimeters high. But by factoring in the elevation, we're getting closer to 2 to 3 meters, 1 to 3, 70 centimeters high for these different clusters of boulders. So these are measurements from 2 different images of the same cluster. And they kind of give us some reasonable idea of how tall these features are. So a little something we need to do for everything else. So a good thing to think about is what do these features look like once we get there? So you can train yourself by looking at the Apollo surface images. You can see house rock in the background. And what does that even look like in a NAC image? So you can see that off to the right here. So I encourage you to look between the two to compare what these features look like from orbit and what they might look like from the surface. So these maps will help us figure out where we're going and what we'll find when we get there. They help us anticipate the local geology for landing. They help us provide spatial information for planning traverses, as well as even potential real-time multiple mission scenarios for planning multiple mission scenarios and decision-making during the mission. So with that, I'll leave it there for any questions.
Thank you, Brent, so much. This is awesome work. We have one question by Jim Skinner in the chat. Nice work. Might it be possible to use both points and lines and polygons for outcrops? Points might not capture the full extent of the accessible area.
Yes. So some of the things I didn't show just due to map clutter is mapping out the length of some of those outcrops with a line. So I do have a mixture of line features that can be used to map kind of some of the more elongate or linear looking outcrops and features. and polygons to map out some of the broader extent of an outcrop. Yes.